Hi, and welcome to Communicate with Channels in Rust. I'm Herbert Wolverson with Arden Labs. We're going to be talking today about channels, which have been in the Rust programming language since pretty much the beginning. They're kind of an unsung hero of the backend. They're used over and over again throughout infrastructure for communication fabrics inside services, often then linked to external services, as we'll talk about as we go through. So if we want to switch over to the slides, I'm ready to go. Okay, this is a well-known quote from Rob Pike, well known for the Go programming language, so I'm crediting somebody outside of our normal ecosystem here. Don't communicate by sharing memory, share memory by communicating. Now, what that really means is try and avoid the spaghetti that you tend to find in a lot of older programs where you have a shared variable in memory that you lock, change state, or if it's an atomic, you can skip the locking part, and then access that from various parts of the program to find out what's going on. It's far better in terms of writing code that you can understand when you come back to look at it later, to take your data, send it from point A to point B in the form of a message, in the form of enumeration, strings, anything you want to send. That's exactly what channels do. They do it really fast, really efficiently. We're going to dive deep into how to use them, how to work them, how to structure programs around them, and how they can help you in day-to-day Rust development. So a little bit about me. I'm Herbert Wolverson. I'm the Arden Labs Rust trainer and consultant. I'm the author of Hands-on Rust, Rust Brain Teasers, and just launching right now Advanced Hands-on Rust, which is in beta with the Pragmatic Publisher. I'm the lead developer on LibreQOS and BracketLib, and I contribute to a whole lot of open source projects whenever I get the chance. Okay, so what are we going to cover today? We're going to cover what is a channel. We talked a tiny bit about that. How Rust models channels. We're going to look at some simple examples using threads. We're going to focus on performance for a little bit because this is Rust, your Rustations. Performance is where we tend to go. I've never met a Rust programmer yet who's happy with a sluggish program. We'll talk about using a crate called Flume to provide multi-producer channels, multi-receiver channels, where you can have lots of sending into the channel and lots of receivers getting messages from the channel, automatically load balancing if you wanted to. We'll talk about using one-shot, a special type of channel that only ever lives long enough to send exactly one message. We'll talk about sending really large bits of data. We'll talk about some of the other ways that you can use channels. We'll model data flow with channels, so how you can connect channels to disparate parts of your program that could be completely independent of one another, even developed by separate teams inside a monolith, and easily then scaled to a different services architecture if you need to scale out horizontally. We'll talk about how you can use channels in some interesting ways, like bridging the divide between synchronous and asynchronous programs, how channels can be really useful in FFI, that is foreign function interface, when you need to communicate with systems that aren't written in Rust, but you're calling the code from Rust, or vice versa, and need to provide a way to bridge the data. And then we'll end with going a little channel crazy, putting together a demo of that models backpressure and data transferred throughout a system, and how channels can allow you to make your system almost self-pacing, and with clever orchestration you can come up with a really high-performance, really scalable system. All right, so let's start with a bit of background history, and where else do you find channels? So a channel is literally just a way to send data from one part of your program to another part of your program. Typically, it's crossing a thread domain. So sending data out of one thread and into another. If you're in async, then you're sending data out of one task into another. Channels aren't new. They've been, in 1989, Van Jacobson proposed channels as a way to send data between parts of the network stack. They've been in use in the TCP/IP stack for that ever since. Smalltalk, all the way back in the 1970s, used a similar concept to pass messages between objects. And Objective-C was built around a very similar concept. In those cases, they were all modeling basically the actor model, which is where you have individual components that receive messages in, act on the messages, send replies out. These days, Go has become the poster child for sharing data between Go routines via channels, but it's very much the same principle that was used all the way back when we were programming in Smalltalk and Objective-C. You take some data, you shoot it into a channel, your Go routine does some processing on it, possibly sends it out of other channels, other Go routines, possibly just saves it to a database, whatever you want to do. So a modern channel lets the sender submit messages without blocking, unless there's a buffer limit. So what does that mean? It means that from the sender's point of view, you hand data to the channel, you can then forget all about having sent it, you don't have to sit and wait, it's just there. So you can focus on what you're trying to do, your core mission, and send the data to other other parts of the process so that they can focus on their core mission. It's a great way to divide code, and it was pretty much the big idea behind the original way that object-oriented programming was envisioned way back. Now, I did put the caveat unless there's a buffer limit. When you send into a channel, you're not blocking, but the channel only has so much internal capacity. It's either going to need to allocate some more memory, you have to wait for that, or if the channel's full, you're going to have to block and wait until something has taken the message out of the other side of the channel. Or you can do a check and see, hey, it's full, I'll not send it right now. On the other end of the channel, receivers can pull and activate messages when they're received. If it's threaded and the thread goes to sleep, there's almost no overhead for waiting for a message to arrive in your channel. So again, it's pretty easy to receive the message. So the idea, once again, is that it's easy to get the data in and then focus on the part that you care about, which is processing the data, doing something cool and interesting with it, and not worrying too much about the plumbing behind the scenes. The plumbing has been built really well for you and does the job great. And modern channels come in all shapes and sizes, large number of flavors, all built around making sure that you can model the data flow process that you need for your program without needing to worry too much about the internals getting down into how the thing actually works under the hood. So baked right into Rust is std sync mpsc, multi-producer, single consumer. Now, what does that mean? It means you can have as many producers, that is, people sending into the channel, as you want. You can only have one consumer. So all the channels go to one place, you're all sending into a single thread. Sometimes this is a great pattern. It's not always the pattern you want, so a lot of other channel types have appeared. The crate crossbeam has become pretty much the de facto standard. You will find it used all over the place. It implements an excellent multi-producer, multi-consumer channel, meaning you can have as many senders and as many receivers as you want. Now, this isn't email. You're not specifying, I want to send this to receiver number 3. You're specifying that I want to send this, and one of the receivers is guaranteed to receive the message. It's an important distinction because you can increase the number of receivers as you need to help you scale your system. We'll do just that. I personally am a big fan of the Flume crate, which is another high-performance multi-producer, multi-consumer channel system. But I find it particularly nice because the ergonomics are great, it adds a lot of observability options, and it supports both synchronous and asynchronous Rust out of the box, so it's almost no effort whatsoever. If async is creeping across your program, you're getting more async to switch your channels over to use it. Another really popular channel is One-Shot, which is a very specialized, super lightweight channel that will only ever live long enough to send exactly one message. We'll show why that's useful in a little bit. My first thought when I heard it was, why would I ever want to do that? And then I realized the answer is actually quite a lot. On the async side, Tokio includes some channels that are built right in. It's got a multi-producer, single consumer, mpsc, in Tokio Sync. It's also got Broadcast, which is a channel that sends to everybody who's subscribed to the channel, and you're guaranteed to receive those messages in order. Very useful if you need, for example, very useful if you need to I apologize. I was asked if I could see the chat, and the answer was no, I couldn't, but now I can. Sorry about that. Now I can see the chat. So Tokio Sync mpsc is just the same as the Rust std sync mpsc. Broadcast sends one message to everybody who's listening. It's super useful if you want to, for example, send a simple message saying, we're quitting, do all your shutdown. very useful if you have system notifications that need to go everywhere. And one-shot, also implemented for async. The sync and async versions are pretty much the same with with the same crate providing both. And Flume, like I said, is natively both synchronous and asynchronous. Okay, so now we've done a bunch of theory, let's start to look at some code. So let's have a quick look at a very simple example of a channel. So we in our main function, we're creating the mpsc channel. It returns a tuple with the transmitter and the receiver, splits them so that they're easy to use. We make a thread, and we're just going to receive a single message, rx.receive. We'll block the thread until such time as a message is available for receipt. Then it'll return. I'm unwrapping because this is just demo code. Normally, if this fails, it means the channel went away. Channels automatically close themselves, and if you try and read from a closed channel, that will give you an error. We send the message, hello world. We join the thread, and again, I'm unwrapping it. And the reason we join the thread is to make sure that the receive thread sticks around until it's done. So this is a seriously overcomplicated way to print hello world, but it does give you a nice overview of how you can use channels in your threaded programs, and it doesn't get a lot more complicated than that. You can replace receive with try receive if you want to see if you can, send with try send. You can do try. You can obviously catch your errors on the receive, but it's very straightforward, very simple, and it's absolutely worth learning, because this is a great way to replace everybody's favorite static atomic bool, am I quitting? So even if you're just occasionally polling, do a try receive, is there a message telling me to quit? That's a whole lot cleaner than suddenly having to try and share static global variables across your whole program, especially in Rust, where the borrow checker and lifetime systems can make that a little more complicated. Now, there's a lot of things we want to note about that program, though. First of all, I was sending a string, but you don't have to. You can send anything that implements the send trait. I'm personally very fond of sending enumerations to indicate that I want you to do this command, that command, whatever. You can even send function pointers if you want to, as long as they don't capture local scope, because that will cause you lifetime issues. And you'll find, if you dig down into how some of thread pool systems work, that's what they do. They're actually sending function pointers, sending code to execute over a channel so that other parts of the program can execute it. Tremendously powerful. The multi-producer part means that you can clone TX as much as you want. It's designed for it. You won't pay a massive overhead at all. It's what it's built for. Works really well. Like I said, the channel will close itself if no senders remain in scope. So if you ever run out of transmitters, the channel will close. And also, I wanted to point out, I used the constructor here, channel. That is a sure way to have me look over your shoulder and cough politely in code review. That means the channel is unbounded. If you only have one or two or a few messages that you're ever going to send, no biggie. The channel will grow as needed for whatever capacity you send into it. But if you keep sending to it and your receive side can't keep up, you will eventually run out of memory. Your operating system will kill your process. Bad things happen. So quite often in production, you want to be using a sync channel with a bound listed to explicitly limit the size of the message you're using, and that way you won't run out of memory, and you can use backpressure, which we're going to talk about in a little bit, to coordinate your program flow. So let me pull up example 2, bounded mpsc. So this is much closer to what you're actually likely to use in production. Instead of sending just a string, in this case, I've defined an enumeration, given it just the one command. mpsc is bounded. It is in Tokio. In the standard library, you can do, yes, there is a constructor for it. I believe it's channel, but I don't have it in front of me. So we make the channel, and you'll notice I've set specified sync channel, specified the bound, so we're not going to ever have more than 65,536 messages in there. We're going to make 64 threads. We clone the transmitter because you can have as many transmitters as you want. And each of these threads is sending in thread X message. The messages are pretty boring because our num really only allows you to print. Since we've cloned everything and the original TX remained in scope, I'm dropping it. This is actually a really common bug. I've seen memory leaks caused by it with ARCs quite a bit, where you send everything clone and never move the original, so the original may not fall out of scope. Very easy to do. Then we'll just receive messages. The reason we made sure we dropped the original in this case is that when there's no more transmitters, the channel will close, so allow it to close. Wait for all the threads to finish at the end to make sure we're running cleanly. And this should do what we would expect. And there we go. We are sending tons of messages through each of the threads. You'll notice they're not quite in order. Channels don't make any guarantee that the messages will arrive in any particular order. That's fine. Just wanted to make a quick note because people in classes ask me this all the time. 64 threads is absolutely not a problem on modern systems. Linux can handle tens of thousands of threads. Last time I checked my thread limit, it was in the 60,000 region on my workstation in the office. I'm not quite sure what the macOS limit is, but again, thousands of threads aren't going to give you a huge problem. If you look at your process monitor these days, you already have thousands of threads running. Modern schedulers are built to expect that. Okay, so let's dive a little bit into channel performance. I put together a little very simple benchmark program, example 3, and we're going to share the GitHub with this when we post the video. It's pretty much the same program again, but now I'm sending an instant in time to, so we send when the message was created. I'm saving them out to a CSV file. I'm not going to run this because I'm running thousands of them. Instead, I went ahead and plotted out the performance. So using the standard library mpsc, the best case was an amazing 40 nanoseconds. That is ridiculously fast. The worst case actually happens at the very beginning when the channel first allocates memory. The channel seems to lazily allocate, so the first time you start sending messages into it, that's when it starts to allocate the RAM that's needed. So your first message, that was diabolically slow at 3 milliseconds. So again, most of the time not a problem. But the P90, so the 90% most frequent performance, was around 5 microseconds, and that's really, really good. So if you write a program that sends sparse messages just occasionally, you will find that your receive time is around 14 to 16 milliseconds, and that's actually a magic number. The reason for that is that is the default tick time at which the Linux scheduler notices that, hey, this needs to wake up, activates it. So on the receive time, though, a minimum of 585 microseconds. That's really good. P90 of 13 ms. Okay, so this particular benchmark where we're slamming things pretty hard, running in debug mode, it's not going to be quite enough to be sending messages on a 60 frames a second game. Good enough for the majority of enterprise systems. Cypher asks, how would 2 times CPU NUMA affect these benchmarks? And the answer is that you will have to test it for your use case because it changes pretty much every time. If the receive thread pretty much has a core to itself and is never being interrupted, then you're not going to have to worry about the context switch delay for receiving messages. So that's perfect. On the other hand, if you're crossing the NUMA boundary, then you are going to be subject to your CPU's synchronizing delay, getting the data from across the bus from one to the other. In reality, that tends to be fast, but it's not going to be quite as fast as if they were both on the same core and one was idle. But so interpreting these charts tells you a lot about channels and a lot about how channels are useful. So sending is very, very fast. And that's really important because quite often you'll see a pattern where you have one program that's receiving data from a lot of different sources. Might be Internet of Things devices all sending data home. Might be that you're hooked up to a big industrial system that is collecting data and trying to send it upstream. I talked to one fellow at one of the national laboratories. That's exactly what they do. Huge amounts of data come in from their hardware simulations. Channels act as the regulator to send it to the rest of the system for processing, use backpressure to slow down or speed up. The worst case is always bounded by the channel filling up or having to allocate memory. So if you're going to be running something that is extremely time sensitive, warm up your channel beforehand by having a message that you send out that exists purely to activate the channel, get the memory allocated, get it going. Try and figure out your channel bounds. We're going to talk a little bit about that in a bit with backpressure. Most of the time, though, waiting 14 microseconds to pass a message between parts of your program is pretty acceptable unless you're writing something life or death like the braking system on a car. Now, receive time is always longer. Unless you've very carefully set up your thread core arrangement, there's going to be context switch time. Can't do a lot about that without going async. And the graph is strange. You'll notice that when there's more to do, the channels are speeding up. That's because we're if the thread won't actually go to sleep if there's more to do. It'll call receive. It won't have to block. It'll say, hey, there's more immediately. You can keep going straight through. So channels are arguably a little faster if you keep sending to them. In answer to the question, the Git repo for this will be posted in the comments right after this goes up at the end. Okay, so let's hop over to async land. Example 4. So this is pretty much the same exact thing that we had a moment ago, but I'm using Tokio or Tokio. I've created a mpsc channel. The little bit of syntax that always trips me up is that Tokio channels are bounded by default. Standard library channels are not. So Tokio encourages you to do the right thing. Once again, we're sending everything in. Instead of using thread spawn, we're using Tokio spawn. If you don't know the difference between that, a thread is a full system thread. Tokio spawn just makes a task, which is a very lightweight, effectively a green-threaded item that is scheduled by Tokio and not by the operating system itself. And the biggest syntax change here is that you have to await on receiving because we don't want to block the thread. We want to tell Tokio to wake us up when there's something for us to do. This tends to give you significantly improved overall throughput because Tokio doesn't have to jump between threads. Sometimes Tokio will use one thread per core is the default, and sometimes your tasks will end up on other cores, sometimes they won't. But on the sender time, our minimum send time is 218 nanoseconds. So that's actually slightly worse than the sync time. But we had a median of just 774 nanoseconds and a P90 of 2.6 microseconds. So you can send messages in async land extremely fast. And on the receiver side, the shortest delay was 508 nanoseconds. Again, absurdly fast. The median of 5 milliseconds and a P90 of 8 milliseconds. As I said on the slide, async is really made for channels. They just line up beautifully. If you look at how Go or Erlang or similar work, they spawn multiple threads per core, and they spawn a thread per core, and then run a task executor on each of those. That's how green threading works. That's what Tokio is doing too. And so a lot of the time, there is no delay whatsoever for core synchronization because you're executing on the same side. There's no context switching because Tokio's executor runtime remains in control, so it doesn't have to change a different thread. It just has to look at its list and say, hey, here's the next task. Off you go. And polling to see if data is ready to be sent is an extremely fast operation. And so Tokio really lets you make the most of sending data between your around your system, just like it does on other languages. But you get, Rust, bare metal, extreme performance. And so the best part here is that when I was running those benchmarks, I deliberately benchmarked having more submission threads than I had physical cores. So I'm deliberately overtaxing my CPUs. I made sure that there would be contention by doing so with a single receiver. And best of all, I was in debug mode. The performance when you start having only a single sender with no contention, only 2 async tasks, and no thread contention, still a single receiver, and actually optimize the code by running in release mode, starts to look pretty darned impressive. 45 nanosecond minimum time, P90, so most common, on the send side of 172 milliseconds, and a P90 receiving of 2.2 microseconds. So that gets you, yes, Tokio Spawn does not need to be joined. It begins executing on the runtime. You can, however, join them if you want to make sure that you resume execution when they're done. So when you're, I don't know if any of you read Reddit, go over to r/rust. The first question everybody asks on why is this slow is, did you remember to run in release mode? And that's a question you should be asking yourself every time. If you did forget to run in release mode, you're losing a whole lot of performance, but only some of this performance gain can be attributed to the better compiler settings. A lot of it can be put down to carefully managing the contention so that there's less opportunity for things to be blocking. But don't ever forget to use release mode if you care about the performance. Even if you're writing a device driver, channels are usually sufficiently fast. I recommend if you dig into embedded Rust at all, you will find that async is increasingly popular as a way to model interrupt events. You'll find that channels are quite useful as a way to pass data between parts of the program, even in no STD embedded land. Okay, so what about multiple receivers? Let's have a quick look at example 6, mpmc. Just as a note to channel creators, I would appreciate it if you made more pronounceable terminology. Okay, so we're using Flume. Flume is very similar to Crossbeam in terms of operation. I chose Flume for this particular one because it gives some observability that is a lot harder to get out of Crossbeam. We're going to be, and when we start getting into some of the more fun graphical stuff at the end, you'll see why that's useful. But once again, you create a Flume channel just like you do all the other channels. It's nice and consistent. Flume bounded, so I've specified an exact channel size, makes a transmitter, makes a receiver. Now the big difference here is that now we have multiple senders and multiple receivers. So the both the TX, the transmitter, and the RX, the receiver, are designed to be cloned. Cloning them is very lightweight, it's not going to hurt you, and it's intended for you to do that to allow you to scale your system as needed. So once again, making 64 threads, and each of them is going to be receiving a cloned transmitter, sending into it, so pretty much the same as it was before. But on the receive side now, instead of just one little receive thread, we're actually cloning it 4 times, putting each of the receivers in its own thread, and then each of the receivers will receive a message. Now, when you send a message, it will go to one of the receivers. It won't go to all of them. It's not a broadcast. It's just guaranteed to be received by one of them. So this gives you an immediate way to scale up the receive side. So you can have more receivers receiving work as available, scale it up based on the number of cores that you have in your system, and you can start to get a really high-performance system put together. Obviously, we don't need particularly high performance to print out, hey, I received a message. Whoop. As you can see, messages very fast. We're receiving, each of the threads was receiving approximately 1/4 of the messages. It's load balancing between them. There are some create feature flags that allow you to change the scheduling behavior. We're just using the default. Very straightforward to use. It's opened up a lot of possibilities. You can decide exactly how much of your CPU you want to dedicate to receiving messages from other systems. And you can keep nesting these, so you could have each of these sending into channels further down the line. We'll model that in a second. You can even dynamically add and remove receivers if you need to. So if you have some sort of complicated system that is monitoring current load, you could spawn more receivers because they're needed. You could recycle some of the receivers later. That gets a little more complicated, but it works really well. So when I started benchmarking this, we had a best case receive time of 8 milliseconds, and so it has slowed down. But that kind of makes sense. We're still in threaded mode, but now it's got a little more work to do because the message comes in and it has to be sent out between multiple, picking multiple queues, picking the right one to send it to. So you've added some complexity, you've slowed down the overall receipt, but you've increased the volume of what you can send because now you can have multiple channels, multiple receivers, each handling the workload as needed. So once again, it's a trade-off, like all things in engineering. If you need to send from point A to point B as fast as possible, it's a whole lot easier if you don't need a traffic cop in the middle determining which point B is going to receive it. On the other hand, if you need to be able to handle a lot more traffic, now you can have multiple lanes. So, summarizing performance, once you've got guaranteed contention, guaranteed core exhaustion, and complicated 4x receiver, you still have fantastic submission times with 49 nanoseconds median. Your receiver times 7 milliseconds, not quite as good, but we're oversubscribing sufficiently that get a bigger instance is actually a fair solution at this point. But once again, you are handling an absolute metric ton of messages. Very nearly said something I'm not meant to say on stream there. An absolute metric ton of messages. And so most likely in your program, your channels are not going to be the slow point. Okay, so what if you want to reply? Cypher in the chat mentioned this. If you are implementing something similar to the actor model, which is the idea that you have say an async task that receives messages, does some processing, it's quite likely that at least some of your operations are going to want to send a reply back. The one-shot channel is fantastic for that. And so we're going to look at example 7 actor, which will spawn a task listening for messages. If it receives data, it increments a counter. If it receives a query, it replies with the current value. And lovely absence of locks. Okay, so we have our async function I'm calling actor. We're setting a counter to 0. You notice it's just a regular mutable counter, and the reason for that is that we're not sharing that in any way. Because we're acting purely as a single task actor, we don't have to worry about synchronization or sharing with other tasks. Receives the message. If the actor wants to record some data, we just add it to the counter. If we want to get the data, well, let's go and have a look at this. Get data, the parameter is a one-shot sender that is set to send U64s. And so inside the actor, we can just call sender send, and let's have a look at that from the client side. So we make a one-shot channel. Once again, it's the same. There's no point in specifying a bound for a one-shot because a one-shot is exactly one shot. The bound is always one message. We submit our request to get the data, sending it the transmitter that we've made. So I talked about how you could send anything, pretty much anything that implements send over the channel. This is a good example of that. You can send channels over channels if you want to. It's channels all the way down. Then we await the one-shot receive. And because we're in async land, all these awaits just mean tell Tokio that we can wait until something is ready for us. So everything naturally stacks, flows down. If you're doing a lot of tasks at once, gives Tokio a chance to make sure all of them get some CPU time. But that gets you a very basic actor model in just 20 lines of code where you've got all the things the actor can do to find a receiver that is just a simple loop where we're looping forever, matching on receiving messages. You'll find that while let is also a very popular pattern there. I wanted to make it explicit in showing that there could be an error here. So if the channel, for whatever reason, has gone away, we're going to break. Sometimes you'll want to note that, hey, this actor died for whatever reason, or recycle it. And it becomes pretty straightforward to use it. We record data 1,000 times, 1,024 times, put some sleep in async tasks, and we also periodically query the data just to see that the task count is going up. So the proof is in the pudding. Go ahead and run it. And so as you can see, all running asynchronously, very simple actor model. Channels make this much easier than trying to handle passing complicated lifetimes around. Particularly if you are used to working with references, you could be passing an arc and using automatic reference counting to make sure that your data gets destroyed when all of your actors are done with it. You might just be moving the data into the channel, making sure that when it's done, it gets deleted. So you're doing all of this without garbage collection. And that's part of why you're getting such great performance, but it's mostly why you're getting such consistent performance. You don't get the giant spikes that you find in some garbage collected systems when it's time to take out the trash. So lots of reasons to use actors. One is that they are a great way to make code self-contained. So from an organizational point of view, it's quite easy to have one team or one person working on an actor, and you define all of the inputs and outputs. Gives you a nice clean way to separate your code. It's very nice for isolating state into self-contained systems. Ties in directly to the Rob Pike quote from the beginning. So you're not changing shared memory, you're not changing shared state, you're communicating the change, and that way the place that manages that state is responsible for that state. It greatly simplifies the amount of locking that you need. Sometimes when you've got multiple receivers, you'll still need some locking, but at least now it's contained. You're not having to worry about, hey, some part of my program, several thousand lines away in a different module is holding this lock and I'm getting deadlocks. Nope, you don't have to worry about that because you're nicely containing it, keeping it all squished together. It's a lot easier to reason about. And honestly, performance is great, but understanding what you wrote when you come back to it 3 months later is even better. And even better than that, if you hand it off to somebody else to work on and they understand it, then you have succeeded in life. So this isn't always the best pattern for fast data processing pipelines. And by fast, I mean nanoseconds are something you have to worry about. So if you're doing something down on that level, maybe channels aren't going to be the right answer. But for pretty much everything else, channels fit really well. LibreQOS, my pet open source project, uses this heavily. We actually have data arriving from kernel ring buffers at a rate of several thousand per second, feeding them into channels. The channels then go through processes that accumulate the data, and other channels feed that to user interfaces to update state periodically as needed. We also use it for the Blackboard pattern. So sensors submit lots of data. Periodically, we read all of the center state, fuse it together. You could do it without channels, but you will just end up with spaghetti. Channels give you a nice way to at least define the shape of the noodles and have the receiver for each of your spaghetti noodles in one place. So when you have multiple channels, select is pretty much your friend. Let's have a quick look at an example for that. And select as a macro is pretty much become a de facto standard for this type of thing. You'll find that Go has a select model, Java has a select model. There's even a C++ select if you can, if you like Boost. So in this case, I'm using the select macro from Tokio. Has a slightly odd pattern matching syntax, but what select is saying is operate on whichever one of several futures returns first. So you combine this with channels, and now we've got a channel that's giving us sensor readings. So if we get a sensor reading, we increment the accumulator. If we get a control channel reading, most likely that's going to be telling us to quit. So now we're listening on two channels, and we will respond to whichever one has a message. Now, there I would give you a couple of warnings with the Tokio one. It does not guarantee fairness. So if you have two busy channels coming in with select, there's no guarantee that it's not going to mostly favor one of the two. If that's the case, I would re-architect around something like Flume, which can help you with that. Also, cancellation is an interesting hot topic. If you want to start a fight, head over to a Rust forum and claim to have solved the issue of async task cancellation. It's well worth the fireworks. Don't do it under your real username, though. You'll probably eventually get yourself banned for starting that fight. When multiple async tasks come in, the other await requests get canceled. So what happens if there's a message that comes into the queue in that brief time between you receiving it and the other one and that await being canceled? And the answer is you can lose a message. That's not always great. That's not always fatal. It depends on your requirements. But bear that in mind when you're defining it. If losing any message at all would be fatal, then you are better off doing try receive to see if there's a message for me and operate on that than you are using select, which may end up losing a message. And so using the select macro, my computer at work averaged 57 million messages per second, sending through the little system in debug mode. Managed approximately 4 times that in release mode. Not a very big computer. It's actually an Intel that has the overheating problem, so it's currently underclocked. The overvoltage problem. So it's currently underclocked until my new motherboard arrives. Didn't try and optimize anything, but while we were sending those 57 million messages per second in debug mode, I was consuming 3 megabytes of RAM. And that's really not bad at all for such a high-performance transmission system. Ties in beautifully with other Rust programs. So if you're using Axum for web, I have on a webinar last year, I demoed that you could serve out tens of thousands of JSON requests per second using 8 megs of RAM. Well, we can probably afford to add 3 more to be handling just that many channel messages. Excuse me. So in our example so far, we've been sending small data. Now, this is a little unfair because CPUs are fantastic at sending word-sized data around. The cache is very much optimized for sending small blocks of data. Channels are also moved by default, just like everything else in Rust. References will actively make your program painful because you have to be able to prove to the borrow checker that whatever you send a reference to, it will be still around whenever whatever receives the message receives it. And that's problematic. You start getting into static lifetimes and suddenly you're back to spaghetti. So here's the secret. Living in a box, living in a cardboard box, or an Ark. If you have huge data, you don't necessarily want to move it into the channel, because doing that will cause the compiler to generate a mem copy, and possibly more mem copies depending on the structure of what you're sending. So put it in a box. Now, a box is a pointer to your data and a size, so effectively 128 bits on most modern systems. Really small. But now, when you move the box itself. You don't move the contents of the box. The box stays in your heap in one place. I've managed to speed up systems by over 100 times with this trick before. Your data won't be moved, won't be mem-copied. The pointer will move. And guess what? Modern CPUs have enough registers that they can do that without even... so the compiler can optimize it out to be a simple register switch. Practically instant. The box will still be cleaned up when it's no longer in scope. But a box has a single owner. That's kind of the point of a box. It's the equivalent of a unique pointer in C++. You have one owner. You've populated the box. You give the box to somebody else. Now they have ownership of it. So if they drop it, or it'll be destroyed. If they pass it to somebody else, ownership moves on. That's often great, not always what you want. Sometimes you want to submit the same data to multiple channels so that different parts of the program can operate on it. If that's the case, you can use arc. Arc is a pointer to your data, a size, and an atomic counter for how many clones of this arc currently exist. When you clone an arc, the counter goes up by 1. When you drop an arc, it goes down. When it hits 0, it's destroyed. So making sure that you don't accidentally hold on to an arc you don't need, you can divide your data, send it out through multiple channels all over the place, all through your program, and be absolutely guaranteed that you won't leak the memory because your arc will destroy it when nobody's looking at it anymore. So this solves another part of the problem is, we don't have garbage collection. Well, arc is a form of garbage collection, so yes, we do. So what else could you use channels for? We've talked about using the channels to submit data from... If this is a safe way of working on heap, could box be good enough for STM32s with small stack memory? Honestly, I would have to look that up and get back to you. I'm sorry, I don't have an easy answer for that one. Multi-consumer channels to manage load, capacity, and backpressure. So sending too many messages, filling the pressure, organizing data with actors. So how about stringing many channels together to represent a complete data processing flow? You might also notice if you use gRPC, Tonic models streaming gRPC with channels. They're almost exactly the same syntax. So if you've been using channels and you need to scale out horizontally, it's almost a drop-in change to start using gRPC instead. We're also going to look at bridging the sync-async divide and integrating FFI with other languages. So let's start with, how about you have a pretty common data flow here where you have control messages, multiple sensors, all pouring into some sort of accumulator that is gathering the data, batching it together, forking it off to a data logger, and eventually that sends it to a database, and also forking it off to a system that watches data as it goes through, accumulates state with a view to giving you warnings if bad things are happening. So channels work really naturally with this kind of data flow diagram because a channel represents the links between each of the different sections. And as we've talked about, using arc, you can easily have your data go off to be logged and monitored for warnings. You can use multi-producer to be sending multiple things in. You can use select or tray receive to check occasionally to see if there's a control message that needs to be acted on while handling thousands and thousands, millions of messages flowing through your system. So channels not only fit really well with the coding side of things, they fit really well with the design side of things because they naturally answer the question of what is that line between the two systems. They're a great way to be passing data through. Like I said, Tonic gRPC uses channels internally, and the interface that you have when you're talking to a remote streaming service is a channel. And so now, if your warning monitor isn't scaling, it's almost a drop-in replacement to replace the channel calls with gRPC calls. Very little code will change. And because you've been good and not had any global state, neatly separated everything out, it gives you a very easy way to add some horizontal scaling when and if you start to run out of vertical scaling. Okay, so let's have a look at example 10, sync async. In this one, we're going to make a Tokio mpsc channel, spawn some threads, and use send blocking. Now, the key here is that Tokio's mpsc channel supports both sync and async. And so you can, as long as you keep your async on a separate thread to your synchronous code, use Tokio and async for the asynchronous part of your program. So you see this a lot where you have a system that is mostly synchronous. It's doing what Rust is best at, heavy number crunching, heavy lifting, heavy processing. But you really wanted to have a small networked section whose main purpose in life is to share data with the rest of your program. Tokio makes this quite easy to do, and it allows you to avoid the undue complexity that comes from obtaining obtaining runtime handles, injecting tasks into Tokio, which now is not only complicated, but has a tendency of getting a little bit unstable. So I've got a function called async land. Over here, we're just receiving messages from an async channel, printing out that we received them. Over here, however, we make 10 synchronous threads, clone the transmitter, just like we did before, but instead of calling send, we call blocking send. And what it really means by this is we're in a blocking part of the program. It doesn't mean that you have to wait for it to actually send the message. It means we're in threaded land, not async land. So Tokio tends to call that blocking. Blocking send, submit it into the channel. And then we're just going to make a Tokio runtime, launch it, run the async code. And so this is very simple, and deliberately so, because I didn't want to confuse you with a terrifying example. And you'll notice I forgot to trap closing the thread at the end, but it receives all the messages from the synchronous land to the async land. You can go the other way as well if you want to. So I hear all the time people complaining that the async Rust people and the Rust people don't talk to each other. They do, but they tend to recommend using channels to provide an easy way to connect the two halves of the program together, because async tends to color your program. As you add async, your program gets more and more async. So in FFI, you're not going to be able to send a message directly across a channel between two programming languages. That just isn't going to work. But it's very useful if you want to have a Rust core that's running that is being called from outside. For example, I recently helped make some C# bindings for LanceDB. LanceDB is almost entirely asynchronous and pretty much assumes that you have a full Tokio runtime going with all the bells and whistles. C# is also asynchronous, but it is most definitely not Tokio. It's whatever Microsoft came up with their internal implementation. It's very fast. I don't know a whole lot about the details because I only use C# occasionally. So I wind up with a bunch of exterior function calls that you pass in that lazily create a Tokio runtime. So if there isn't one, it makes one on demand. And then all of the LanceDB calls get passed in by a channel to that. Once it's been initialized once, the runtime stays around, just needs to send messages in. All replies also come out as channel messages, usually often one shot, because there's usually just the one reply, sometimes a full mpsc if you need to be streaming results back, and then calling that back, passing that back to C#. The same pattern will allow you to bridge with pretty much any language. So you don't have to lose the async part of Rust just because you're calling the Rust through FFI, which is inherently synchronous, unless somebody decides to rewrite Tokio in binary compatible version of C++. And that sounds insane, but I talked to a guy at RustConf who said that that's his mission. So maybe one day. starts to look a little complicated, but at the same time, the channels actually make it nice because you're separating concerns out. You end up with a small FFI layer. If you remember, FFI is all about the unsafe word, so you keep that nice and under wraps, safe rest behind it, and as safe as C# ever gets on the other side. All right, so let's have a quick look at example 11, CLI. This is the last of the demos. This is pretty straightforward. It's modeling what we were talking about earlier, where I've created a set of threads that are injecting data into a system, created a layer that is batching them together, created some processors that then calculate moving averages. It's very similar to what you'll find in a bunch of enterprise pipelines. The GUI code I don't want to go into in great detail here because it's a little complicated, but I'm using eGUI. Highly recommend that library if you just... I'll answer Motozai's question in just a second. So if you want to throw a GUI together, give you something nice and quick to illustrate a point, I highly recommend eGUI. It is relatively straightforward to use. It's what's called an immediate mode GUI, so you end up with a lot of code because you're drawing everything every frame, as opposed to the React model where you're updating things and having the GUI update because the underlying data changed. But here we have a system following the dataflow pattern that I illustrated earlier. So we have, in this case, 4 producers, each of them spamming out messages as fast as possible. I'm graphing because Flume will allow me to see the current thread capacity, and we're spamming out messages right now fast enough that we're completely filling the producer thread. So the producers are actually being slowed down. You can see the performance going up and down because they're all having to wait for space to appear in the thread. And despite that, running in debug mode, we're sending a good couple of 100,000 per thread per second on my tiny little MacBook Air. The batch combiners are currently taking these messages. When they receive 32 of them, they combine them together and send them off to the layer 2 processor that is just calculating a moving average. So this is by far the slowest portion, and it's just handling a mere 30,000 messages per second or at a time. If you start adding simulated delay, you can see how the whole thing starts to grind to a halt because the processor is now waiting 0.1 seconds between each of the things it's doing. Its queue is starting to fill up. Backpressure is working its way back up, so you'll see that each of these is slowing down. We haven't had to write any code whatsoever to detect that, hey, there's a load problem. It's just gracefully slowing itself down. The whole program paces itself out to match what's available. Take the delay away, watch everything start to speed back up. If we start increasing and changing the batch system, once again, we're submitting messages. We're making larger batches in each of the batch combiner levels. And you can see that as we do that, the number of messages being processed, getting through to the end, starts to tick upwards. Now, I recommend doing this kind of thing and open telemetry or maybe something more lightweight. I personally like to have something a little more lightweight than OTel for prototyping. OTel is great once you start getting into production. Have run into times where I'm spending more time communicating with OpenTelemetry than I am actually doing any work and slow my system down. But you have to be careful of that. That's always a pitfall. If it's almost like quantum physics. If you look at it for too long, it changes state. But this is kind of illustrative of what you can do, and also what you as the engineer need to start worrying about, because you've got your data flow, you're modeling it, orchestrating it so that each of the layers is sufficiently well fed, sufficiently tied to enough CPU power, but not too much, so you're not sitting idle, is how you scale your system, how you design your system to run perfectly forever and not wake you up at 2 a.m. because things are failing, and also how you identify where some of the bottlenecks are and determine if you need to start worrying about scaling out to additional systems. So more as I asked a minute ago, channels can be used for inter-process communication. And the answer is not any of the channels that are in the box. There's a couple of great crates, the name of which I will have to look up, and I will post in the comments when we're done, that allow you to use a channel-like syntax for actual IPC on the same box, but also most of the good message passing systems like gRPC streams basically use a channel system and then wire the channel to some network code. So it's almost a drop-in replacement when you start wanting to use gRPC with tonic and prost to replace local function calls. And lastly, it's not in this presentation, but if you're interested in doing that, I recommend looking up Ractor. It's actor with an R at the beginning. It is a distributed actor framework for Rust, and Netflix have started making heavy use of it. They had a great presentation on it at RustConf that is on YouTube. Pretty much what we're discussing, but it handles some of the channel wiring for you, and then if you move an actor to another box in the network cluster, it will handle the communication for you. So the answer there is yes, sort of. Okay, that actually brings me to the end, and I wanted to bring up a somber note real quick before we stop. This week, we lost one of our own. I've been working with Dave Tutt on LibreQOS for 2 or 3 years now. You probably not heard his name, but his code actually drives millions of routers and servers. He's behind fqcodal, Cake, and a whole bunch of Wi-Fi code in Linux and also in Mac OS. He's relevant to this talk because he's the one who showed me how to get kernel ring buffers blasting tens of thousands of messages per second into my Rust code, which taught me to hurry up and learn all about what I need to do with channels to handle that kind of load. He passed away this week. We're missing him greatly. He was such a wonderful, influential figure. We even got a message from Vince Cerf offering condolences this week. So I apologize for changing topic. I just wanted to share the love, and we miss you, Dave. Okay, anybody got any additional questions? I did my best to keep up with ones from the chat, so there may not be all that many. And I've lost all track of whether or not I'm late or not because we had the break in the middle. So, and okay, I'm not seeing a lot of questions. I know there's a time limit. There's a time delay. Hopefully, I didn't put you guys to sleep. From the questions, I know at least some of you were listening. So the Ultimate Rust bundle with Arden Labs, if you want to have more than 20 to 30 hours of me talking to you, is available now. Video training, Ultimate Rust Foundations, and Next Steps, both of which talk you through the basics of Rust, from Hello World all the way up to building a distributed Internet of Things network. A best practices collection, Ultimate Rust Best Practices, Rust as a Service. Rust as a Service touches on some of the channel things, but is more about building JSON and gRPC services, how to structure your service cluster. Rust from C and C++, which is very much foundational level FFI to get you going with talking to C and C-like programs and some C++. And a few weeks ago, I was in Miami. I just recorded a few new ones. There's one coming that is focused on organizing your Rust program, how to handle large amounts of data, how to structure your program, divide it up so that it's easy to work in multiple teams and still benefit from Rust. And one on FFI, which gets pretty advanced, digs down into a lot of the gnarlies of what do I do if I'm trying to use a void ** from C and want to try and write something vaguely safe in Rust. Rust has some answers, and that class is my best attempt at answering them. Okay, well, thank you so much for coming, and I look forward to hopefully seeing some of you in more classes. Arden Labs do in-person training, online training, recorded video training, consulting, and hopefully I will hear from you guys. Thank you.